Hello everyone, I'm Alberto Rigo from University of Southern California and I'm presenting our work on contact optimization for non-prehensile loco-manipulation via hierarchical model predictive control. Legged robots have a great potential to interact with the environment in applications such as logistics, disaster rescue and construction industry. Nevertheless, with existing control and planning frameworks, most applications for quadruped robots focus on navigation and inspection, which always try to avoid obstacles even if they're movable. In mobile manipulation, robots can exhibit different modes of interaction with the object. For example, mobile robots equipped with a robotic arm can enable basic manipulation tasks such as door opening, pick and place, and load carrying. However, such setups are limited to small and light payloads due to the force limit of the robot arm and gripper's size. For large and heavy objects, non-prehensile manipulation, such as pushing, offers tremendous advantages. When the object is too large or heavy to grasp, pushing using the whole body becomes one of the few options to manipulate it effectively. In addition, this method also allows quadruped robots to manipulate objects without adding a heavy and costly robotic arm. This is the block diagram of our proposed approach. First, we have a model predictive controller used to optimize the contact interaction with the manipulated object. The optimization variables are the contact location between robot and object, and the contact force that the robot needs to exert on the object. This first NPC optimizes the control variables to drive the manipulated object to a desired goal position and orientation. Then we introduce a unified NPC for loco-manipulation to regulate the contact interaction to track the planned trajectory for the object-robot system. This unified NPC integrates the optimized contact force and location into the conventional NPC for locomotion of legged robots. To expand on the contact optimizer NPC, consider the object dynamics as a single rigid body subject to friction and contact force. These equations are nonlinear, since the moment generated by the contact force is the product of the force times the contact location. We can linearize these equations and write them in state space form to be used as equality constraints in the NPC. Moreover, we include some important inequality constraints on the control input. The contact location is bounded by the object dimensions, and the contact force must be always positive to ensure contact is maintained. To effectively regulate the desired contact force FC and contact location D derived from the contact optimizer NPC, we present the unified loco-manipulation NPC that takes into account these two variables in the control design. In comparison with the locomotion NPC, we have two main developments of our framework for loco-manipulation. Our loco-manipulation NPC considers the interaction force Fc between the robot and the object in the robot dynamics. Therefore, it can regulate the desired manipulation force while maintaining desired performance for locomotion. The reference trajectory of the robot locomotion is also automatically updated based on the desired contact location D, as well as real-time feedback of the object state. Now let's take a look at some simulation results, where we compare our proposed method with other controllers and the corresponding experimental results using our approach on a Unit 3 A1 robot. We want to compare our approach with two other controllers, the baseline NPC by itself and the baseline NPC with an heuristic policy to change contact location. From the videos we can see that only our approach successfully completes the task of following a straight line, maintaining the correct orientation of the manipulated object. Then we look at the experimental results for this task. We can see from the video how the robot makes small adjustments to the contact location on the surface of the box, so that the orientation and position tracks the reference values. Then we look at simulation results for a task, where we want to track a constant yaw rate for the manipulated box. We can see how the baseline NPC fails immediately, having no way of adjusting the contact point. Then, both the other controllers successfully bring the box to the desired location, but only our proposed approach tracks the reference constant yaw rate while always maintaining contact with the manipulated object. We then look at experimental results for this task to finally validate our approach. As in the previous experiment, we can see the adjustment on contact location that are fundamental to track the reference trajectory. In this case, the changes in contact location are more noticeable, and still the robot never loses contact with the box, thanks to the constraints considered in the controller. Thank you for your attention. If you have any questions, you can find me at the poster session on lagged motion analysis and synthesis on Thursday, June 1st, from 9 to 10:40.